Okay. All right, I think we can get started. So let me just hi. So going live in 2 minutes. Say hi if you're out. All right, so right, is font and font size okay. Okay. Okay, cool. Let's get started. All right, so today I thought I'd spend some time to talk about something that's, I guess it's been on my mind for almost a year now. Initially, when we started building out a bunch of different projects, Rust Boot among one of them. While exploring Rust, I began to wonder if, we could, if Rust's type system could be, I actually felt like, if we could have a little more power from Rust's type system, that would be really great, because then we could incorporate some extra, guarantees. So today's talk is going to focus on, as the title says, functional correctness using refinement types. By now, if that title doesn't make sense, you can think of it as a way to say that how can we make the Rust type system, how can we can we actually add more to it? Can we have, can we do more with it, basically? And by doing more, I mean, can we, because today the Rust type system actually offers things like, you obviously memory safety is one. If you're writing concurrent code, you also get concurrency safety using the same concept of ownership and borrowing. But beyond that, you have requirements around functional correctness, which means the logic that you use to, whatever you're using to write code, is that good? Is that, correct? Right? So you basically want to go ahead and figure out whether what we have in the Rust type system is enough. If it's not enough, can we do, can we have something like an add-on on top of it to sort of get this piece that's called functional correctness? Now, of course, I know that doesn't make a lot of sense without explaining what functional correctness is, etc. We'll go into some examples, because one thing that I wanted to note is, I'm not an academic that spends a lot of time researching, programming languages and figuring out things like guarantees and on, certain kinds of functional correctness aspects, etc. Mostly from a programming language perspective. From a user perspective, I'll be talking about this subject today. All right. So let me quickly just check the chat to see if that sort of makes sense. Yeah. So we have Creeman. Hi there. sorry, I remand. Yeah, so I guess, I'll just dive right into it because we have only 1 hour, so I'd like to make the best use of it. So to get started, I actually pulled this blog up that I wrote back in 2020. That's why I said, it's been a while since, this has been on my mind. So initially when we started off, this particular blog that I wrote was when I was working on the early parts of Rust boot and trying to figure out how to put things together, etc. In there was one particular piece that I pulled out and I said, I'll just write a little blog about it so that, it was going to be for my reference. And also, if people find it useful, it's there and probably look at it. So this little snippet of code that you see on your screen is basically a standard Rust function where effectively what we're trying to do over here is we're trying to build the simplest possible bootloader that can anyone confirm? Yeah, okay, good. All right, so let me just sort of go through this again. So yeah, when we started working on the Rust boot project, we noticed that you may be dealing with Rust, but the moment you hit that unsafe fragment, there's a lot of things that you actually have to consider. Obviously, all of that is unsafe, so that's why you put it in an unsafe block. But that got me thinking, what if we had just a little more information within, provided to us by Rust's type system? Maybe we'd be able to actually provide some additional guarantees, right? So case in point, take this particular function, which is basically the boot from function. Now, the simplest way to explain this is it's just a very simple piece of logic that's written for the Cortex-M microcontrollers. The Cortex-M microcontroller architecture, you have an interrupt vector table. The first two entries are the stack pointer and the reset vector. And that's exactly what we're doing over here. We basically cast the integer that is given to us, which is a U32, into an actual address pointer or a memory address pointer, which we call it the stack pointer. And then we also do the same thing for the reset vector. We just increment that integer value by 4 and say, okay, whatever's over there, go ahead and cast that to an address and give me that value. And then the third statement says jump vector. Jump vector goes one step forward to say that I would like you to take the bits that, whatever reset vectors contains, take the bits of that, whatever type it is, take the bits of that and reinterpret those bits as a function pointer, particularly as an external C function pointer, right? So there's a lot of, type squishing and squashing going on over here, which is why all of this is not safe. There's no guarantees for this. And the last two lines that you see, or actually the two register writes that you see, we write to the system control block. That's the vector table offset register. And we also write to the stack pointer, which we just were able to cast in the first, stack pointer statement. Lastly, once we set up that, once we do those two register writes, we are able to go ahead and perform that jump to our reset vector. And then from there on, whatever's at that location, we start executing, correct? So that's what you would normally, that's how you'd normally work with when you work with something like a Cortex-M microcontroller. But if we were to sort of dive a little deeper and pay a little more attention to what we're doing, you'd see that, okay, why is all of this unsafe? Well, we're dereferencing 2 pointers, which is the first 2 pointers. There's 2 raw pointers, they're being dereferenced, and that's by definition unsafe behavior because it's undefined. Anything can pop out of your dereferencing action. Then transmutating a 32-bit integer, which is again the reset vector, to an external C function that's also undefined. We don't know anything can actually happen at that point. The last 2 register writes. Register writes by definition, writing to a register is, so let me also explain this. There's something called which we may not have come across, at least in our conversations, is side effects. This is usually something that you would have heard of if you're dealing with functional programming. But in this case, think of it as if you are actually just writing your own code and your code is like, performing some calculation or some computation, it does not affect the external world, then that's called a pure function, right? For example, you're just doing you just have like two numbers, you want to add them. That addition operation is not going to affect any other state outside of that, outside of what your function is executing, right? But a register write by definition is actually going to set some value in a register, and that's going to affect the external state around it, right? So that's called a side effect. All right. And then there's also something called we basically, whatever we transmuted, which is the jump vector, we're going to call that. We're going to call that function. The point that I wanted to make over here is that function call, which is the jump vector. Technically, our intent was to say that, look, I'm going to jump there, but I'm never coming back. That's it. Once I jump, my function is divergent. It never returns. Okay. We're not being explicit over there. Again, that's that's why all of this is inside the unsafe block. So a lot of these things together contribute to the fact that this is definitely unsafe. But we've gone ahead and done our due diligence. We've looked at everything. We've confirmed that all the values that we are casting and we're transmuting, all of them are perfect. Now, given that this is a small piece of code and Rust boot is not a large project, this is relatively a simple thing. We shouldn't be making mistakes. But what if we could actually make this better? In the sense that, what if we could ensure that the compiler actually told us, for example, we gave the compiler some information and the compiler told us, okay, you just told me that, let's say your stack is within this boundary. In the sense, the stack's memory map is within the memory map, the stack holds this particular region, or the stack sort of encompasses this region. What if we were able to provide that information, and at compile time, obviously the compiler will let us know if you're going to do something that's not right. Okay. Then, although your raw pointers, etc., still may be unsafe by definition, you can still provide guarantees to say that, yep, Rust's compiler may not be doing it, but I have added something on top of it that is doing this checking for me. Okay. That's just an example use case that I'm bringing out. But from there, I started looking at exploring, why can we not, this is the whole point, why can we not actually take a type and say, okay, I don't want, for example, if I was to take the U32 type, so the U32 type by definition says that you've got, it takes any value or any value between 0 to U max, U32 max, whatever the value is for U32 max, any value within that range can inhabit that type. That's essentially what we're saying when we say a U32, right? But if we talk about a stack pointer, we know that maybe the stack pointer starts at 20 million and probably ends plus 256 kilobytes. That's it, right? Now, if we were to define a new type that says this is your type, which is 20 million to this is where to plus 256 kilobytes is the values that you can take. That's an entirely new type, right? Does that make sense? Let me just take a pause because this is sort of the important thing over here. Does that make sense? Okay. All right. I think it does. So that's the idea. So basically, you'd actually like to work with, you'd actually like a little more what do you say, refinement in your types. See, that's the word where refinement comes from. You're trying to say, look, I don't want the U32 type, which has this, entire, it can take any of these possible values from 0 to U32 max. I want something that actually only works for my stack pointer, or I want something that only works for, let's say, some of my memory mapped IO, because we have peripherals in, when we talk about memory mapped IO in our peripherals, we're talking about some addresses in the memory map that if we write to them, we're going to be configuring the hardware and then we're going to be able to work with them, right? So all of these things become very interesting if you can actually say that I have a specific type that I can define that only takes these values and does not take anything else outside of that. If we can express that some way and the compiler can actually type check this for us, that's a really good, thing to do, right? It saves us a lot of work, and it also ensures that we can do a little, we can get a little crazy with it, which is what I'm going to show you with a tool, or rather a project that, a bunch of people have been working on. So I heard about this when I was working on these projects. I actually did some research and I came across something called Haskell. Haskell is a functional programming language. Within that, there was a specific set of people working on something called Liquid Haskell, which I will explain a little more. But I'm not going to talk about Haskell. I'm basically going to talk about the same concept that was applied to Haskell for extra refinement in their types to Rust, and how that's actually helping out, and also probably talk about some examples as well. But so far, does that sort of give us a good idea? Yeah, because I'm going to be spending a lot of time actually talking, because this stuff takes a while to sort of set in, at least initially. But after that, it becomes, using it, once you get to know how it works, that's really the best part, right? So I've mentioned, I think I'm going to share this blog anyway, the link to this blog anyway, but all of what I just discussed is mentioned here. Then in order to deal with all of the problems that I mentioned in the, in the previous section, I basically went ahead and wrote this, right? This is what the Rust boot implementation is for boot from now. So I basically created a type called the refined usize type, within which I'm saying what is the minimum and the maximum given the value. And it's actually going to say, okay, if you want a bounded integer, that means between two bounds, if you want to check that whether or not the value that I passed in is between these bounds, you actually check this. Or if you pass in a single valued integer, which means you can only have an integer with one value that inhabits that type. So by the way, this is just a hack. This is not actually being done at compile time. This is just the thinking behind it, saying, what if we could have this? Because we didn't have that, that's why this is being done. And this is done at runtime, right? We're actually doing a check. We're doing an assert check at runtime and checking to see if this is all happening. What if this could happen at compile time is the question, right? So here's how that, here's what we're talking about. We are basically saying, let's take the stack pointer over here. We say stack pointer starts at a minimum of 20 million, and then 20 million plus whatever 40 is the bound that we have. And then I am basically going to go ahead and pass an address into it. And that address is what I would like you to confirm whether when I actually use this function and if I pass a value that's not between 20 million and 20 million 40,000 hex, whatever that is, then you basically panic, right? That's what the assert macro is going to do for us. If it's not within these bounds, I want you to panic for me, right? So that way I have a little more, I'm still using Rust types over here because I'm specifically using, what's called const generics. That's essentially why I use const generics over here, so that it helps out. And then something similar for the reset vector as well is what we've done. And lastly, if you see, these two are just extra safety pieces that we wanted to write, just to ensure that, you know, we have data synchronization barriers and instruction synchronization barriers before executing these two instructions. The last statement was a jump vector. Ideally, that should basically return the never type, because we're never returning back, right? And then that's essentially what we have over here. So when we do all of this, some level of confidence is there that, okay, my implementation is a little better now. Of course, it's only better because we're doing all these runtime checks, right? We're doing all these runtime checks, and that's what is sort of helping out. And that's why I'm a little more confident that this implementation is better than the previous one that you saw, right? So, but this is happening at runtime, as I said, and that's I was always wondering, you know, can we not do this at compile time? It seems easy. Why can we not do this at compile time? And that's when I started exploring a bunch of different options out there and landed on functional programming, learned about Haskell, learned about liquid Haskell and all of that. Now let's look at how you could solve something like this, address something like this at compile time. All right. So far, so good. Any questions on this part? I'm not going to cover the last part of the blog because that'll make sense after we do some examples with flux, etc. So let me just quickly check the chat. Any questions so far? Right, so I wanted to cover introduction to functional correctness. Actually, it's not much of an introduction. It's just sort of give you some intuitive understanding with an example, and also the use cases that I just talked about. So we've covered those two. Okay, so I talked about the use cases. I talked about memory mapped IO, and then the control flow with bounce checking, the stack pointer, and the reset vector that I just talked about. There's one other thing that I did not talk about, which is we wrote a lot of parsers for our Rust boot project, right? We wrote one for the fit image, we wrote one for the signing tool, we wrote one for the header construction. Now, this type checking is extremely useful when we talk about something like parsers, because inherently parsers are all about, there are no side effects when you're writing a parser, because you're just constructing bytes. You're putting bytes together, or you're parsing bytes out of a constructed header or something like that. So there's no side effects. You're completely, it's a pure function that you can do it within, which means these functions will not go and sort of set some value globally or change something externally, etc. You just given a piece of data, given something that needs to be parsed, you can just parse it, right? And something like this is very, very useful in that case as well. Now, with that context, let me come to what flux is. So since I had to close my browser, I'll just have to pull it up again. Flux Rust. All right. So yeah, not to worry. I've actually done most of the installation of the tools and stuff like that. So it should be fine. So we can just go to the website. So they've got, the project is fairly new in Rust, but in Liquid Haskell, they've got a bunch of different examples. It's really, really useful over there. The same thing can also be done here, because Rust's type system is very powerful, and you'll get a feel for it as well when you start looking at it. So yeah, actually, there's also, we can also try it online. I'll just pull this up and put it to the side, because I do have some examples. I do have some examples for both, which is the ones in the playground. It's called the Flux Playground. And I've also put some of my examples together just to try it out in VS Code itself. Okay. So here's how, let's actually look at, the introductory post on Flux. So The important point that you see over here is, let's start with this statement. Refinements are a promising way. I hope you can see this, by the way. Yes? The font size is good enough. Because I just want to confirm, because sometimes it's too small, sometimes it's too big. Okay, I guess it's good, right? Yeah. So as you can see here, the statement, or rather what's being said over here is, refinements are a promising way to extend type checkers. Type checkers are basically, in this case, Rust's type checker. So whenever you see that, there's a type mismatch or something doesn't really, there is a reason why your code isn't compiling. It's usually the case that, you got your types wrong, you used them incorrectly, or some little corner case that you forgot to think about, etc. Right? So Rust's type system is very powerful. Now, if I'm able to take that information that already exists, that the Rust type system can already provide, and then build some extension, build a tool on top of it, let's just say a tool on top of it that takes that information, adds it to its own piece of information, and then does a little bit of, what you call constraint solving. I'll talk about what that is. Then you can actually come up with something called correctness guarantees for your implementation of whatever code that is writing, that can actually be verified by that tool that you just the tool that you're using. I know that's a lot to unpack. I'll just break it down. But before I go there, let's just talk about this. So you take the information that the Rust type checker already possesses, and then you build your own tool. That tool is going to be using something called a constraint solver and a bunch of other things, techniques, etc. But basically it takes this piece of information and then it sort of analyzes that. The right word is solve, constraint solve, and then says, okay, with the information that's available to me from the type checker and with the information that I have from my tools that I've got, I can say that functionally either this piece of code that you've written is correct or is not correct. Now, I'm not talking about things like memory safety or concurrency safety. I'm actually talking about functional correctness. So with that said, let's actually just jump to an example, all right? So everybody can see my browser, the VS Code instance. Yes. Okay. So let's quickly look at this. If you see here, I have, your normal Rust function. This is basically a public function called, I'm calling this make 10, which is basically you're returning the value 10. So I'm saying 5 plus 5, it should return 10, correct? Now, if I just sort of comment this out and, if I do something like this, this is good, right? There's no problem because according to the definition of this function, it doesn't take any arguments. It returns an i32 value, correct? So an i32 is basically the negative and the positive halves of your, maximum 32-bit values, right? That's kind of what you get, right? But that's the whole point. Rust's type system cannot catch this. It can tell you, okay, the type signature says I take no arguments and I return an i32. So this perfectly type checks, right? There's no Rust analyzer errors, obviously. Nothing is problematic over here, right? But if, for example, if I did something like this, that would be an error, right? Because obviously I'm saying it's an i32, but I'm returning a unit type. If I don't return any value, that's a unit type that I'm returning in Rust, and that doesn't match up with this signature, correct? So that's like, the trivial thing that we all know and love about the type system. We don't really think about this, right, a lot, because we've been using it for a while. We don't really think about these things. But This, I'm trying to make 10. And in this trivial example, I've actually made a 9 and I'm returning that, and that still works. So there's no guarantees from Rust as far as functional correctness is concerned. What you intended to do functionally, you wanted to return 10, but you returned a 9, right? There's no guarantees that the Rust compiler can provide. But if you were to apply something like flux on top of it, which is nothing but using the procedural macros method, you can basically take that function, take the type checking information in there, and then do your thing and come back and say, okay, wait, what? There is a squiggly line over here, right? Now, of course, there's if you sort of look at it, you will see that post condition might not hold, right? This is where the whole idea of refinement types really shines. What's happening over here is I've annotated, or rather decorated, annotated, whatever it is. I've annotated my function with a macro to say that, okay, we have a make 10. And in this case, make 10 is basically an additional layer on top of that. What I want to say is, it's a function that doesn't take any arguments, but it returns an i32. Specifically, it returns an i32 that must return the value 10. Right? See that difference? Because in the world of types and values and all of that stuff, this type is actually different from this. Does that make sense? I'll just quickly check the chat. Does that make sense? Okay. I guess it does, right? Yeah. So that's essentially what we're saying over here. If I was to change this to, exactly 10, then this type checks, right? Now I can actually ensure that at compile time, I didn't run anything. I didn't compile anything. I just didn't, go ahead and say cargo run, etc. Nothing. I'm just using flux to tell me whether or not the code that I've written is correct. And I'm not talking just about, basic Rust, whatever type checking is included in Rust. I can use Rust's type system and build on top of that to say I can actually provide functional guarantees. Now I've written a function that will always return 10 all the time. If it doesn't return 10, then what I wanted is not function. The functionality that I wanted is wrong, so it should not sort of type check. That's what I'm trying to do over here, right? Now, so let's take another example. All right, so this one's a little more complicated. I've actually put in a little bit of work over here. So if you see this is basically, so let me just first of all, I'll just sort of comment this out, and I'll say I'm trying to calculate the max value. All right, immediately if you see over here, there's an error that's popping up, and because this max is dependent on this. Anyway, let me actually show you. If you look at this, it's basically I give you two values, two i32s again, and I'm saying I will return an i32. That's the Rust function or signature of the function that you're using over here. So what do? We just compare both of them and we say, if x is greater than y, then go ahead x. Otherwise, just return y. Right? Very simple. But what I actually want to do over here is, I want to ensure that a couple of things are actually, I want to ensure that this implementation of the maximum of two values is actually functionally correct. This is not enough. Just writing this is actually not enough. And let me explain why that's not enough. So if I was to do something like this, which is I write a flux signature. A flux signature is nothing but on top of your function, you want to add more information to it. You're saying that, okay, it takes two values, which is x and y. It returns an i32. I'll just talk about the P over here. Just give me a minute. P is the predicate over here. But I32, the return value, let's talk about that first. I'm imposing a condition over here saying that I'm not just going to accept, whatever return value you give me, as long as it's I32, I'm okay. No. I want the return value to satisfy this post condition, this entire post condition. Okay. The entire post condition has three, basically three Boolean values. One is the returned value, which means whatever I get out of this function, which is v, it must, so let me just take the last two first, and then I'll take the first one. V must be greater than the value that you returned from this function, must be greater than or equal to x, number one, and v must be greater than or equal to y. So either if it returns the x or the y, it must be greater than, the x and the y. Make sense? Yeah. I think VS Code Windows is stuck. No. You can see lines 10 to 20, right? No, I think it's working. Let me just scroll a bit. Oh. I'm not too sure why things are hanging. Okay, I think it is stuck. Let me just restart this again. Yeah, sorry about this. I don't know what's going on. Okay, let's just go back. Okay, now is that good? So I'll just highlight this. I think you guys should be able to see this. Yeah, cool. Okay, so now if you look at it, you have, I call this the post condition, right? The post condition is basically, I started out with whatever inputs, then I ended up with whatever outputs. So the inputs form my precondition, the outputs form my post condition, and there's also something called invariance, which we'll get to. But this is effectively what I want my output to conform to. Whatever I get as the I32, that value must meet all of this conditions, right? So it must be either, if you've probably returned the x, then either it's equal to x, or because it could have been a y, so it could be greater as well. And then it is either greater than or equal to x, or it is either greater than or equal to y, right? It must be that. Then you have this third, or this first condition that you see is called P of v. Here P is defined as something that takes an integer and returns a Boolean value. So functions that take functions that actually return Boolean values are called predicates. Okay, that's why here what we're saying is the precondition for this function is we are saying P of x and P of y. That means x and y should be some integer. That must hold first. They must be two integers. They can't be, something else, basically, right? You want to ensure that is the case first, to see if which one's greater, or which one's sort of, to compare two values, which is x and y, you need to ensure that you're actually passing in two integers. So Of course, you can say that, the Rust type system will take care of that, but you want to ensure that the values that are passed in are actually true. That's the first thing. You check that, and then you say, okay, whatever is returned is also, and fits my definition of this post condition. Right? Does that make sense? Yeah. I can repeat it. I mean, this does get a little bit, you just have to think about it a little bit when you look at it, and then it'll sort of make sense. Okay. So now let's just say, let's just go for it. Let's just say I wrote a function that says max test, and I'm just going to test this. Okay, I'm going to say max 4,5. Right? I'm just trying to test this. I seem to be getting, oh sorry, yeah, this is a Rust error. So if you actually think about this, this works, right? Technically this works. 4,5, if I pass it in over here, it's going to actually check all of these, the preconditions and the post conditions, check both of them and ensure that, I'm good over here. And then obviously because it type checked over here, I can definitely use it. Whatever value I pass in should just work, right? It should just work. There's no question about me checking whether this is working or that is working. It should just work. That's the first point. The second point is, let's say I want to mix and match stuff over here. For example, what do I mean by that? I mean to say, this function that I wrote, let me actually sort of remove these things first. So I added a few more pieces just so that, I could, let me, okay, that's fine, but I'll just sort of change this. And I'll say, all right, let me go with 4,5. Right? Oh, sorry. I'm just going to say go with 4,5. Right, now you see that it says post condition might not hold, right? This makes sense now because over here, the max function was working. There's no problem. It works. But here, I seem to have added another flux signature on top of my existing one for max. I'm saying for modulo max, ensure that the output is, so max works out. Max actually checks out. That's fine. But whatever max is returned does not match the output, or sorry, the post condition that I'm providing over here. That means the post condition is it must be an even number. Whatever I'm getting as the output, as the post condition, it must be an even number, right? That's the other condition that I've added over here, and that is not satisfied. That's why the post condition does not hold, right? So, but if I went ahead and did something like this, that'll work because 4 and 6 are both even, and this condition gets satisfied, right? And that should technically work. Make sense so far? Okay. Any questions on this? It sounds relatively simple, right? Of course, because these are very simple examples. When you actually apply them to something like your parser like where you have, that 256 byte array that we have, the bytes that are going into it. You want to ensure that, you're not messing it up in some way or some case that you could probably have not thought of. There, this level of this additional type information that you are able to express makes a world of difference in building out functionally correct code. Right. So the last example that I actually want to talk about, and just sort of wrap up with the examples, now that you have a better idea about this, let's take, see this thing? I've got assert. By the way, this is not the assert macro. This is a function that I've just defined. It's a normal, regular Rust function. If you look closely over here, it's got a flux signature on top of it. The flux signature is basically saying it will accept a Boolean value, but the Boolean value must be true. Only if it's true, I'm good. Otherwise, I'm not good. All right. Now, how can we use that? It's very interesting. The way I can use that is I write a function called increment, and I say, look, I want you to ensure that, in this case, this is also an interesting one. It takes the flux signature, says that the argument that I take is x, but I want you to ensure that whatever is returned is x plus 1. Of course, Rust's type system, there's no way to say that. You can't say that. Using flux, you can actually say this, saying, am I returning x plus 1 or not? If I'm not returning x plus 1, then the functionality that I intended this function is not conforming to that functional specification that I have in my mind, at least. Right? So this is very straightforward. This will type check. Now, but if I did something like this, let's say, that's going to throw an error. See, post condition will not hold. Right? That's effectively what is happening here. Now I just apply these two together and I say assert increment 1. So if I give increment 1, it's basically less than or equal to 2. So it's definitely equal to 2 because if I give you 1, you're going to give me 2. Right? That makes sense. Now, if I try and assert this again for the value 2, if I add 1, I'm supposed to get 3. But I'm saying it's less than or equal to 2. That's not right. That should technically fail because it's a combination of two functional or two particular specifications that we're applying, one for the increment, one for the assert. The first thing that happens is this thing, increment 2 works. You'll get a 3. But 3 is not less than or equal to 2. So that's essentially what this is saying. The precondition over there is not holding. That means what I'm passing in as input does not hold. Right? Sounds trivial, right? Okay. All right. So given that, let me actually move to the last part, which I wanted to sort of put together some examples and then talk about the Rust refinement type checker. Now, I just also wanted to sort of jump to the playground so that, you have a few more examples that you can use. So for example, there is a bunch of options over here. You can have a refined option, which is basically like the refined use size that I was talking about. But this is more refined in the sense that you don't accept, all the possible values you have. So if I just click on this, an option usually has a none and a sum, but we are trying to say over here that the nuns and the sums, I further want you to constrain those types. It should not be any sum or, probably any none as well. Right? So you can apply that over here, and I don't have time to actually go into that completely, but effectively we can apply this to things like vectors. Algebraic data types are nothing but option. Basically, in the functional programming world, those are called sum types and product types, etc. But in our world, in Rust, we're basically calling them options, or rather enums. Basically, you can just call them enums for now. And then recursive types, recursive types is types which have them, that means the same type as one of its fields. So that's, you can also use them there as well. A lot of this stuff is very, very interesting to read about. For example, Flux uses Rust, as I said, it uses a lot of the Rust type system to help it, come up with these solutions to the specification that you are putting on, or you are decorating your functions with. So you basically write a specification, decorate your function or your piece of code with that, and then you let Flux run and type check, and it checks to see, given the information from your type checker, which is the Rust type checker with what your Rust signature is, and given the specification that you've provided me with, which is the additional information I have, I put those two together and I run it through what is called a constraint solver. And that constraint solver is automatically going to figure out, okay, all of these inequalities and equalities, I'm going to put them together, and I'm going to figure out whether or not there's a solution to this. If there is a solution to this, great, I'm going to put it over there. If the solution that I have says that, there is a corner case over here that you're not considering, which is why, you should consider that, then you can go ahead and add more information to your specification saying, I want this exactly. Right? So that in a very, very high level overview of what we're talking about, refinement types for Rust and the places where it could actually help us. All right. And now some of this is, obviously we need to work on actually applying this, and the use cases I've already mentioned, which is the parsing stuff, the memory mapped IO stuff, the control flow based bound checking stuff, all of that. Okay. With that said, the last part I think I can talk about, because there is enough time, is this. So before I jump into this, any questions? All right. Okay. Cool. So, so what I want to actually talk about was, spent quite a bit of time on this, this exact problem. Everything was very interesting, had a little bit of time. So I explored this space of formal methods. So formal methods, there are roughly, or broadly speaking, two different categories. One is what you call the interactive theorem provers, and the other one is called the automated theorem provers. What you just saw with Flux is what we call, is basically the second category, the automated theorem prover category. So I'll just spend 2 minutes on this so that you have an idea. Some of the examples that you will see are things like Daphne, Pharmacy, Tamarin, etc. All of these are very much in the what you call in the C world. I think in C++ as well. Not too well versed with that, but yes. Now you've got a lot of tools that people are working on, the formal methods community is working on, which is basically speaking things like Prusty is one good example. Then there's something very similar to Prusty, which is called Croissant. Then there is Kani from Amazon. That's not exactly, it's not a, so Prusty and Croissant, they're called deductive verifiers. They pretty much use the same method. You provide specifications like a precondition, a postcondition, a loop invariant, etc. And then you can get one, and then you say go. And then the backend tooling that they've got will start working to say, okay, can we solve this problem that we have in front of us? And then says, okay, I've type checked it. Here's something that you need to fix, or it's good to go. So this part, that's the automated theorem proving part, right? So as I said over here, you specify constraints, as you can see over here. You specify constraints such as type refinements, predicates, which you just saw, which are functions that return Boolean values. Quantifiers is something that I've not shown you as an example. These are things like for all, etc. But okay, it's not important. And then invariants. We didn't have time to cover this as well. But basically, this is how you write your specifications. You've seen the first two, which is the refinements and the predicates. You saw that, I can say that my input arguments must meet these conditions. My output condition must meet these conditions. Those are refinements. Then predicates are what you saw with the max function. Quantifiers and variants, we can talk more, at a later point. But they also make up the specification. Using all of these tools, you can actually write a very concrete specification to say, my function must do this. I'm expecting this to happen. If this does not happen, tell me in what cases it does not happen, so that I can refine my specification. Then that's exactly what happens. You provide constraints. So all of these things that you just saw here, which is this, x is the input, x plus 1 is the output, which is a constraint. You're saying, I want only this. I don't want anything else. Those constraints are converted into mathematical formulas at the back end. That's what these tools do. And those formulas, there are what we call SAT solvers, which is satisfiability or SMT solvers, you can call them, satisfiability modulo theorem provers, or whatever they're called. But basically, it's just a fancy word for saying that there are these constraints that I've provided as a specification. I want you to put all of them together and satisfy the whole equation. Now, the entire thing is a little more involved. We can get into it, but those solvers are Z3, CVC4, this thing, EICs as well. I've never worked with that. But so I've got, as part of as part of Flux, Flux uses Z3. So I've got Z3 installed. So Z3 is an actual solver. It's an SMT solver. By the way, it's not just used by Flux. As the Z3 SMT solver is widely used in many places, including things like, security, vulnerability assessments, etc., where people, black hat hackers or white hat hackers or whoever they are, they could also probably be using it for things like finding bugs, using something called symbolic execution, etc. But anyway, just to let you know that these are automated theorem provers, or rather constraint solvers. Their goal is very simple. You give them a bunch of constraints in a mathematical format. Its job is to say, okay, I will try and solve this. That's it. And the speed with which it does that, and how innovative it is in doing so, etc., is what all the PhDs work on. But anyway, so that's the idea. You specify, you write your code, and then you verify. That's pretty much your automated theorem prover. The only actually a big drawback is that because it's actually pretty simple and you can actually use it today in your code, you're limited to how well you can express the specification, because there are things that you cannot really express, saying I want X, Y, Z, etc. Now that's where the interactive theorem provers come in. Here, it's not automatically proving something for you. You get to sit with a tool called a theorem prover. The theorem provers are things like Agda, Cork, Isabel, Lean, etc. You start writing a proof, then it keeps helping you, saying, okay, this matches, this doesn't match, this works, this does not work, etc. But the same thing again, you start writing your spec, and then you keep going through it. Here is where you can be a lot more expressive in terms of the specifications that you can provide. And this is where you use what's called usually it's called a dependently typed, programming language, which I will not get into. Maybe at a later date, if we have any time. There's a good one that I really liked, which is called Idris 2 specifically. It's very nice. But of course, there's also, in case you're interested, my suggestion is also to say, probably look at Lean as well. Lean's come a long way in terms of, so Lean is a functional programming language. Idris 2 is a functional programming language. Both of them have dependent types. Dependent types offer a lot of this flexibility, saying you can write that specification really well. When you write a good specification, great. And that specification can be resolved, great. Right? Okay. I hope that makes sense. I hope I've not lost everyone by now. Okay. Any questions before we wrap? I think we're sort of on time, but 5 minutes over. Any questions? Hope this was, or at least interesting, I think. I think when we start actually working with it, you'll see like, you'll feel really good about solving these things, like writing the right specification to get the results that you want. That'll be the best part. For example, we're going to be implementing this for the parser, the multiple parsers that we've written. And you'll see that there'll be a lot of work that we can do. Of course, one point is none of these specifications are actually going to go into production, etc. You'll just want them to be part of your CI. They're not actual Rust code. Rust code remains the same. Your specification will determine that. Okay, cool. Okay, so that's a very high-level overview of what functional correctness is. How we can use refinement type specifically to talk about, to improve the correctness of our code. All right, so Nirmala says these tools help to define the specifications. Okay. I think the question is about whether or not these tools help us define the specification. Yes, absolutely, because as you can see over here, some of these functions are just examples, trying to give us an example to say, okay, you want to refine your your specification. For example, in compare max, if I just removed this, I'd pretty much get a statement saying, okay, something's missing. I don't have enough information to solve this. Something is missing. The post condition will probably not hold because there's a scenario over here. What are we trying to do over here? I'm trying to get an exact value of 10 as my output. After I take the max, I can get any value actually, right? So that's why it's saying, why don't you tell me, can X do, can X be greater than 10 or not? If it can, then your post condition will not hold, right? So these tools help you define the specification as well, right? Hope that answers the question. Okay. I guess it does. Right? Any other questions before we wrap? Oh yeah, we're sort of 8 minutes over, but fine. Okay, I guess not. So that's it for today. I hope this was insightful. Maybe when we write a full, when we use this fully, I guess that will be more interesting as well. So when we get to that point, I guess I can share more information. But thank you for today and have a great day. Have a good weekend. Bye.